In my chemistry classes, I try to set aside some time the day before a test so students can ask questions about the material in that unit so that we can review that material before they actually take the test. That's what this lesson is about, where students ask questions and I respond to help them prepare for the test. Of course, the only question I don't answer is, would you go over everything? Don't do that, don't have time. Okay, so you got to ask me specific questions that you want me to cover. Okay, so what I was requested to do was to go over nuclear equations, basically. You specifically mentioned alpha particles. Let's say that we've got polonium-210. You need your periodic table for this, because I'm not going to just do it for you. I expect you to do what you can do so you can build strength, okay? It's just like athletics. Okay, if you're going to get good at something, you have to practice. If you're going to build muscles, you've got to work out. And so if you're going to get good at this, so you do well on the test, you've got to practice. Okay? So I've given you the atomic mass, which identifies which isotope of polonium this is. Now, there are always more than one isotope of any element. Every element has multiple isotopes. Some are stable and some aren't. And of course, there are some elements, anything above lead, there are no stable isotopes. They're all unstable. But for a lot of elements, there are both stable and, for most elements, there are both stable and unstable isotopes. Okay? This is polonium-210. It's one of those that doesn't have any stable isotopes, but that doesn't really matter here. All we're trying to do is figure out how to write alpha decay, okay, for an equation here. So we need to know, first of all, what's the atomic number for polonium? Okay, you should have at your periodic table and find the atomic number for polonium. If you're not doing this, you're not helping yourself much. 84. Okay, so for those of you who are doing it, great, you figured it out. Just in case there's anybody that doesn't know, what you do is you look on your periodic table and you find the element we're talking about here. Here's polonium right here, 84. And the number we're talking about is this number at the top. That's the atomic number, and that identifies the number of protons, and that's what we put at the bottom. The top number is the mass. The bottom number is the atomic number, or the number of protons. And so the difference between this number and this number is the number of neutrons, because the mass is both neutrons and protons. So to find the neutrons, we simply subtract this number, the protons, from the mass. Okay? So what we want to do is to write an equation in which we have alpha decay. So you should already know what an alpha particle's nuclear formula is. Please write that here, and then also find out what the element is that remains once this alpha particle has been removed. Okay? So let's practice that. All right? So if you haven't done this already, make sure you pause the video and do this problem, and then you can see how it's done. So an alpha particle has a symbol that looks like this. Okay? Now, on a lot of occasions, you'll find alpha particles simply written as He for helium, because an alpha particle's nuclear symbol, at least in terms of its mass and its atomic number, is the same as a helium atom. Okay? But the difference is an alpha particle has no electrons, and it comes out of the nucleus, where a helium atom doesn't actually do that. But very often you see it written that way. So the atomic mass is 4, the atomic number is 2, just something you should know. And then what we need to know is what's remaining over here. So what number added to this next mass over here equals 210? Well, that's obviously what? 206? Okay, so we're going to look for 206 here. Okay, and then down here it's kind of the same thing. What number added to, there's a plus sign here, what number added to this 2 will give me 84, and that would be 82. And so what we do is look on the periodic table and find element number 82, and 82 is lead, and we just identify it as lead. Does that make sense? Okay. Let's suppose that I give you one, well, you mentioned this this equation we talked about here, okay, where I give you sort of blank spaces. Let me give you this. I'm going to give you this and 238, and we're going to have 2 and 1 here. And I'm going to have 93 and 238 over here. We're going to have 1 and 0. Now that's all. That's enough for right now. This is an intermediate step. There's actually another step that takes place here. Okay. So you have to finish the remainder of what's missing here. So we're missing an atomic number here. We're missing the element symbol or particle symbol here. I'm going to put that plus sign there a little bit close. Let's move it over just a bit. Really should move the whole thing over just a bit. That's what I should do. Make a little more space. So you have room to write this particle symbol here. And then we're going to have a plus sign. And we need another particle. Well, actually, we need something in this big box here. And then I gave you a 1 and a 0. And then I left this part blank. Okay, so you have to figure out what goes in those spaces. Okay, so you should be able to, what you do is you just figure out what you know. Once you plug in everything you know, you should be able to figure out the rest. Okay, so until you plug in what you know, the rest is going to be kind of a big question mark. Well, let's do that first. I'm going to pause the video and let you work. Okay, so we have uranium, and uranium's atomic number is 92, and so our atomic number, our proton number goes down here. The particle that has 1 proton, and there's only one, is some form of hydrogen. Okay? This mass number up here means there's 1 proton and 1 neutron, which is the form of an isotope of hydrogen called deuterium. Okay? The element that has an atomic number of 93, neptunium. Okay? Okay? The particle that has a mass number of 1 and an atomic number of 0, a neutron. And so what we've got to do is figure out what are we going to do here to get all this to work out. Well, this is 238 plus 2, so the mass overall on this side is 240. Right now I've got 238 and 1. Okay, so right now I've got a mass of 239. So how am I going to get another mass from just what I have here? Put a coefficient 2 out in front. And now it's going to be 240 over here. That's the mass. Okay, let's look at the atomic numbers and see how we worked out. 92 and 1 is 93. 93 and 0, or 2 times 0 is still 0. It's still 93, so that works out. So it all works out. Does that make sense?
They want to put another neutron thing there, like 1 bit.
Well, no, I could pick copper. Iron. So iron is in the 4th row of the periodic table. Okay, so we know we got to go through 1s, 2s, 2p, 3s, 3p, and 4s before we get to iron in 3d. So 1s has got to be full. 2s has got to be full. 2p has got to be full. Or 1 in each box and come back and pair them up. 3s has got to be full. 3p has got to be full. 4s has got to be full. And now we get to the section where we find iron. Iron is in 3D, and there's 1, 2, 3, 4, 5, 6 more electrons. Okay? 3D has 5 boxes because there are 10 elements in that section representing the addition of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since you can only get 2 electrons in a box, that means you must have 5 5 boxes. And you have to have all the boxes, even if some of them are empty. And we need 6 electrons. 1, 2, 3, 4, 5. You put 1 in each box and then pair them up. Okay? And so that's the orbital notation for iron. The full electron configuration, and guys, I'm going to remind you again, because I noticed that some people didn't do this already, you have to have the symbol and the colon. That's required. Okay? So this is 1s2. You just count the number of electrons. You have 1s, and the 2 becomes a superscript. 2s, 2 electrons in that sublevel, 2s2. This 2p has 6 electrons in the 2p area, the 2p sublevel area, so we're going to just put 2p and 6. Then 3s2, 3p6, 4s2, and then 3d6. Now, for the abbreviated version, also called the kernel version, or the shorthand version, even the noble gas electron configuration, we're just going to find the next lowest noble gas and take that electron configuration out and replace it with the symbol for that next lowest noble gas in a bracket. So the next lowest noble gas has this electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, and that is argon. Argon's right here. Here's iron, and you just count your way back: 26, 25, 24, 23, 22, 21, 20, 19, and there's a noble gas. Anything in this column is a noble gas. So there's argon. We're going to take that part out and replace it with a symbol for argon in brackets. Now all that's required: the symbol for the element, the colon, the brackets, and the symbol for the noble gas. And then you just finish out the remainder of the electron configuration: 4s2, 3d6. And that's the shorthand version of the electron configuration, also called the noble gas version, also called the kernel version, also called the abbreviated version. Yes.
So you would like now you put your fingers there and you're like,
Mm-hmm.
6, you do that to the end.
Argon's electron configuration is this. If we were to write out argon's electron configuration, it would look just like that. It'd be argon, colon, 1s2, 2s2, 2p6, 3s2, and 3p6. Now, if you get stuck on the test and can't remember what part to take out, write it out. You know, why say pencil graphite and then make a bad grade on the test?
That's what I'm saying, but that's the closest noble gas, so that's why you want to put 4s or 3d6.
Right. That's exactly right. Now, while we're here, you didn't ask for this, but while we're here, let me give you the electron dot notation. Okay? So that's just a symbol for the element, and you count the number of electrons in the highest primary energy level. Well, those coefficients like this 4 and this 3 indicate primary energy levels. So how many electrons in the highest primary energy level of iron? How many? 2. We just need 2 dots. And which of the 4 sides you put it on doesn't matter. You're going to imagine a square around this thing, and you're going to put your dots in the middle of the side of each of those squares, as many as you need. So if I just need 2, I do it there. If I needed 4, I put 1 on each 4 sides. If I needed 6, then I start to pair up on 2 of the sides. Yes?
Why are you 2 again?
2 in the highest primary energy level. 2 electrons in the highest primary energy level. That's 4. There's no coefficient number larger than 4. Okay? So 4, there's 2 electrons in 4. Here's the highest energy level. That's a lower level. That's 3. This is the highest energy level, and there's 2 electrons there. That's why I got 2 dots. Okay? The shielding effect is what causes, among other things, causes atoms to be smaller as you go across each row of the periodic table. So let's take a look at this row right here where sodium is. Sodium is a larger atom in terms of how big its electron cloud is than magnesium. Magnesium is larger than aluminum, which is larger than silicon, and so forth all the way over to argon. It's the smallest one in that row, smallest atom in that row. So what happens in the shielding effect is that as you add each energy level, so here's the nucleus, here's your first energy level, okay? And every time you have an electron in here, in any energy level, that electron, because it's moving around, is creating an energy field, okay, an electromagnetic field. If you have electricity running down a wire in this direction, it creates a magnetic field around that wire. If it's going in the direction of my thumb, it creates a field that goes in the direction of my fingers. Okay, it's called the right-hand rule. Okay, and so if I run electricity this way and back the other way, then the field going this way cancels out the field going that way. Okay, and that's why coaxial cable is used for TV signals or even radio signals sometimes, because it cancels out the electromagnetic interference. All right, but you need that interference because that right-hand rule stuff is also why you receive radio signals from the air, why your cell phone works. Okay? All right, back to this. So every time there's an electron moving around, it's creating a magnetic field, which makes it harder for the neutron, or protons rather, in the nucleus to hold on to those electrons. But if you add more, as you add more protons to the nucleus and electrons without adding an energy level, so you're going to be in the same energy level, then you're able to pull it in tighter. So if I go to the next level and add more electrons to the next primary energy level, and the first electron I put out here, it's harder to hold on to that one electron because it's got to penetrate through, if you will, the magnetic interference existing here. That's the shielding effect. So the first electron's harder to hold on to. As I add more protons to the nucleus and more electrons to this level without adding another level, then I can pull that level in tighter and tighter, making this atom smaller. So as I go across each row of the periodic table, that's what I'm doing. I'm adding more electrons to the electron cloud without adding more levels. I'm adding more protons to the nucleus. So it's able to pull those levels, the outside energy level in tighter, okay, and shrink the size of the atom as I go across each row. Okay, that's sort of the short version, descriptive version of the shielding effect. All right, so in terms of describing the way that orbitals are arranged in an atom, okay, when we start at the nucleus. Okay, so this is our nucleus. All right, starting with the nucleus, the first energy level we get to after that it has only one sublevel, and that's the S sublevel. So here's our nucleus, and we've got a spherical shape for our S sublevel. Okay, so that's 1s. Okay, and it's spherical. All right, after we get past 1s, then we get to the second primary energy level. All right, and the second primary energy level has a 2s level. Okay, so 2s is going to be outside 1s. So 2s is out here like this. Okay, 2s. All right. Then once you fill 2s, you start putting in 2d electrons. Okay, and 2d electrons have what we do it in here is a double balloon. Okay, so we say it looks like this. So here's one balloon, that's one orbital, and here's another balloon, that's the second orbital. I'm sorry, this is all one orbital. That's one node, this is one node, this is another node. Okay, and so in the P sublevel you have three of these things, three double balloon shapes. So that's one of them. Here's another one. And so the last one has to be coming out toward you, and then the other node is back behind. So we draw it like this. And the third one, and one of the back's going to be kind of like that. Well, that's a little hard to see or tell what's going on because there's a lot of lines overlapping. So what we got to do is kind of get rid of the lines in the back. And we usually do that with dotted lines so you can still see where they are, but they're kind of hidden back there. All right, does that kind of make sense to you guys when I do that? What's going on? Now all three of these d orbitals make up an energy level. It's the d sublevel. Okay?
Oh, that's like an orbital notation, like the D.
Yeah. And so I'll kind of put dots in here to show how this is kind of hidden back behind here too. All right. Does that make sense to everybody? What's happening here? All right. Now this also happens when we get to the next level. You get to the third level, you have the same sort of thing. All right, but what I'm going to do here is I'm going to show you how they're all arranged. Actually, you know what? We got something else here too we could show you. And that is what the actual shape of these orbitals are. Because it's only the top half of the orbitals in the d sublevel that actually exists. Okay? So the top half of this one, more or less, is what actually exists. The top half of the one that's down here is the part that actually exists. The top half of the one that's sticking out in front is the only one that actually exists. The top half of the one that's over here is the only one that actually exists. Top half of the one that's over here is the only one that only part that actually exists. Okay? So that's what the actual orbitals really are. Okay? Yeah, so what I'm going to do is I'm going to take all that and I'm going to go back through here one at a time and show you how it all plays together. Okay? Alright, so there's the nucleus. There's our 1s sublevel going out from the nucleus. Okay? Then we go to the 2s sublevel from that. So that's outside 1s. Then we've got those balloon orbitals we have looking at there. Okay? And then we've got what is the actual shape of those orbitals, which is only the top half of that. See what I'm saying? And so if we go back to the 1s level here, okay, you can see that, well, let me go one more page. You can see how the top half fits outside that 1s sublevel. See what's happening? So the p orbitals don't actually exist inside the range where 1s exists. And that's why you have just the top half down here. Does that make sense to you? Which is what all that drawing stuff is about. All right.
All right, will we have to, when we do the nuclear equations, will we have to say this fission, fusion, or nuclear?
Well, you might. It's possible. Okay, so fusion then is when you're taking two smaller particles and putting them together, forcing them together to make a larger particle. Okay? So if I have a smaller atom and I put it together with another smaller atom, okay, then I can fuse them together to make something that's larger. Let's say I'm putting together lithium. Well, I'll put lithium down here since you asked about having equations. Lithium, and I'm going to fuse lithium with boron. Okay? And so lithium has an atomic number of 3, and a boron has an atomic number of 5. And I need to have, let's see here. Let's say I've got a lithium that has an atomic mass of 7, and a boron which has an atomic mass of 11. Okay? I'm going to put those together, and if I have a 3 and a 5 here, and I'm going to fuse those together, let's say what we're going to do is, in addition to putting those together and making that, I'm going to end up with one extra neutron on the end. What's going to go here? Okay, so 3 and 5 gives me 8. Atomic number 8 gives me oxygen. And what's the mass that's going to go up here? It's got to be some number added to 1 gives me 18, because 7 and 11 is 18. So it needs to be 17, okay, which is a stable form of oxygen. Okay, oxygen has 2 stable isotopes that I'm aware of, and that's 16 and 17. Okay. Actually, I think it might have 15 might be stable, but I'm not sure of that. So yeah, there has to be more 15 than 17, I think, before the average atomic mass to be as low as it is. Yep.
Why do you have a 2
Well, hold on, we haven't done this one yet. This is fusion, okay? All right, so let's say I'm putting lithium and beryllium together, okay? So I'm fusing them together, all right? And as a result, I'm making oxygen, which is a larger element, plus I got a little neutron over here, okay? So when we put them together, it actually ends up spitting out that neutron, but you actually write it as a plus sign, okay? So here's our lithium, here's our boron rather. This is the oxygen here, and there's our neutron. Okay? And that's describing fission. Okay? Now, very often we have an intermediate step. We don't, like when we're fusing together.
Wait, that's fission?
I'm sorry, fusion. That's fusion. When we're putting together, say, hydrogen, that's deuterium, 2,1H. So there's one particle. And tritium, 3,1 hydrogen, that's tritium. You put those together, you get an intermediate step. Because initially you get them together, but it only sticks around for the tiniest fraction of a second. And that then ends up spitting out helium, which is 4,2, but you get an extra neutron left over. And neutron, remember, is 1 and 0. That's a little bit large for a neutron because it should be smaller. Yep. So this is fusion.
Like if I just had the equation, how would you like determine for this fusion? Like if I had that.
Two smaller particles making a larger particle. You when you say larger particle, you kind of ignore the little tiny things that get spit out in the process. You know, you can get beta particles out, you can get gamma radiation out, you can get neutrons out when you do fission. And that's what happens here. We get a neutron out here too. Okay? All right, now fission then is splitting the atom. So let's say we have uranium-238. We'll put uranium-238 down here. So that's a really large atom. Okay? To make that split, I need to add a neutron onto it. Okay? And the reason is that 238 is pretty unstable already. But you put that extra neutron on there, and what's unstable starts to get even more unstable. Okay? So the nucleus of the uranium atom is not static. It's not a hard kernel in the sense that you think about a kernel of corn being hard. What it is it's wiggling around and twisting and stuff. All right, so when we're writing this like an equation then, we've got to put a neutron here. What's the atomic mass for neutrons?
1.
Atomic number? 0. Okay? Now it's going to split up. And let's see if I can find, I want to get the exact numbers here. All right, so let's say we get this really large particle, which is going to be barium. And this really large particle, which is going to be krypton. And we're going to get some number of neutrons out of this. We'll have to figure out how many to put over here. Okay? Let's say what we're going to get. I don't want to put a plus sign there. It should be an arrow down here. So we're going to have barium. We're going to have krypton. And let's say we get barium 142 and krypton 93. So you figure out the rest. What? What is it? 56? Okay. The atomic number for barium is 56. The atomic number for krypton? 36. Okay. 56 and 36 equals 92. So we've got all the atomic numbers taken care of. So whatever else we have must be neutrons because this is the one that has that 0 atomic number. Okay? So over here we've got 238 and 1. That's a total mass of 239 over here. Right now we've got 142 and 93 for a mass. So we've got 200 what? 235, and we need to have 239. So how do we get 4 more mass units? 4 neutrons. And neutrons have an atomic mass of 1, atomic number of 0. We need 4 neutrons.
So in fusion, you're going to start off with...
All right, so patterns on the periodic table. Here's the SP, D, and F sublevel regions. Okay, now you got to know that helium, when you talk about SP, D, and F sublevel regions, helium is not in the S or the P sublevel region. It's over here in the S. So I moved it over here. Okay, so that's the SP, D, and F sublevel regions. This is the one that's going to help you to write orbital notation, electron configurations. All right, it also helps you write electron dot notation too. Okay, all right. Representative elements. Okay, these first 2 columns, these last 6 columns, those are the representative elements. All right, and we talked about the sublevel regions here. Then there are some specially named regions of the periodic table. This first column here, except for hydrogen. Hydrogen is not part of this. That's called the alkali metals. Okay, it's all one family, all one group. This first column, because all columns are either called families or groups, but what we identify as the alkali metals does not include hydrogen. Okay, then the second column, all of them, all those together are the alkaline earth metals. Alkaline earth metals. This is alkali metals and alkaline with an N-E on the end. Alkaline earth metals. This whole section here is transition metals. This next to last column over here are the halogens. The last column, including the top one, is helium. That's all the noble gases. And down here we have the inner transition metals. So those are specially named regions you need to know. We said there are special names for all these columns over here, but we don't expect you to know it in high school. Okay? The oxygen family's all you got to call that one right there. Okay? Then the carbon family, a nitrogen family, then the carbon family, and so forth. They do have special names. The oxygen family is called the chalcogens, but you don't have to know that. Okay? Remember that? Okay? All right.
So we need to know all of those individual parts.
Yes. So here's our metal and non-metal regions. Metals are everything over here on the left side of this stair step. Non-metals are everything on the right side of the stair step, but including hydrogen. Hydrogen is not a metal. It doesn't belong over here when we're talking about metals and non-metals. It belongs over there. So when we're talking about SP, D, and F sublevel regions, SP, D, and F sublevel regions, helium gets moved over here. When we're talking about metals and non-metals, hydrogen gets moved over there. Okay? Then all those elements that touch that stair step on 2 sides, with the exception of aluminum, those are called metalloids. They behave like metals sometimes. They behave like non-metals sometimes. Okay? Then atomic size. I was asked a while ago about the shielding effect. This is why it is we have this pattern of atomic size. As you go across each row, they get smaller. The size of the atom, the electron cloud gets shrunk down as we go across each row, so the atomic size is smaller. But as I go to the next row down, go across each row, as I go down the column, then you're adding more primary energy levels as you go down. So they get bigger as you go down. Okay? Then we've got ionic size. An ionic size follows a similar pattern, except that where we go from positive ions on the left side to negative ions on the right side, they go from being smaller than the atom and getting even smaller, smaller than the corresponding atom, getting even smaller as they go to the right because of the shielding effect, to the point where we're adding electrons over here, and suddenly they're getting huge and then smaller. Okay? So that's the ion size pattern. Okay, then we've got electronegativity. All right, now electronegativity, lower left, higher upper right, but there's no noble gases in this pattern because there's since these noble gases don't bond by sharing any kind of electrons, then they don't have any electronegativity, so you take them out of the pattern. Okay? First ionization energy is how much energy you have to put into an atom to remove an electron, the first electron. This is the first ionization energy. Same pattern, low down here, high up here, but you can remove electrons from a noble gas. So we include the noble gases in first ionization energy. Electron affinity is the energy given away by an atom when it gains electrons. So this is the energy it takes to remove an electron, the energy you have to put into an atom to remove an electron. This is the energy you get out when you put an extra electron on there. Since noble gases don't want to accept any extra electrons, there's no electron affinity. You leave that out of the pattern. Okay, you mark it off and say that's not part of the pattern. But it's lower down here and higher up here. Okay? And there's one other pattern. I don't seem to have that drawing here.
That's all we have.
So the pattern of reactivity. Now let me say this. There's a lot of ways to determine what is one element's reactivity compared to another. And depending on how you're defining it will shape how you figure out the pattern of reactivity. Okay? This is a general idea of reactivity, not designed to be specific about one definition of reactivity over another. But what we have is we have really high reactivity over here in the first column. This is high reactivity here. Okay? Noble gases have almost no reactivity. There's a couple of them that'll react a little bit, but we just about leave those out of our list. But the halogens over here, they also have high reactivity. High reactivity. Okay? But now the precious metals, low reactivity. That's why they're called precious metals, because they pretty much, for the most part, don't corrode. Okay? And that's where you have silver, platinum, and gold down here. Okay? So you guys should remember where that is, all right? That's kind of important to you. Okay? All right, I know this is stereotypical, and forgive me for being so, but I mean, in a stereotypical storyline anyway, girls want it, guys give it, right? Silver, platinum, and gold. That makes sense?
Yeah, buddy.
Okay.
Golden egg.
That's my song. You rap Snowman singing.
What? Snowman sings that song?
From Rudolph, isn't it?
Oh, really?
Silver and gold.
All right, and I'm probably there's probably some girls in here that don't care about silver, platinum, and gold. I know. All right.
You can sell that song to me.
What?
You can sell it to get money.
You can. That's right. Yeah. Somebody gives it to you, and you don't. You break up with them. You can go to the pawn shop or something, or the jewelry store and sell it. You're right. Okay. But that's the pattern. Okay. But listen. I'm not trying to be stereotypical. I am trying to bring this to your attention because it helps you remember it. If I say it that way. Yes. Okay? And it's probably true for most girls and most guys, but not always. All right? To be fair. Okay? Got it? I don't care about having things made of gold particularly. All right? I don't care,
Yes, you do. Yes, you do.
No, I don't.
Don't tell it,
How much jewelry am I wearing on my hands?
You got a ring on.
I got one, but that's for a particular purpose, okay? I don't have no bling here, okay? All right, so we're going to do the orbital notation for selenium. You have to write the element symbol. It's required. Get points for having it and lose points for not. Selenium is in the fourth primary level, row 4. 1, 2, 3, 4. It's right here in the fourth row. So we're going to be filling up all the primary levels before 4 and filling up all the sub-levels that we come to before we get to selenium. So we're going to fill up 4s, 3d, and partially fill up 4p where selenium is located. Okay, so this is the s sublevel region. Helium gets moved over here to the s sublevel region. Okay, everything in these first two columns then with helium there is s sublevel region. This is the p sublevel region right here. This is the D sublevel region here. Okay? And we just kind of work our way up the periodic table. It's like following the yellow brick road, only we're following all the elements by their number. Yes?
What do you think is the highest element that we go to?
In this class?
Yeah, like on our test, or like that we would have to do.
Lanthanum.
I mean, that one.
That's the
Yeah,
last.
do that one then.
That's the last element you come to before you get to an F sublevel down here.
Yeah, can we,
You want me to do lanthanum instead of selenium?
yeah, I mean, 'cause I need to know like how far it is.
All right. Won't be much difference, but that's
Can
fine.
you do kernel overtake tonight?
I will do all of it.
Appreciate it.
Okay?
I think Charlotte said
You're right.
so. So do you want to take right what you just write?
I guess we're going to do lanthanum.
I like your overall.
So we're going to fill up the first primary level that only has an S sublevel, and there are 2 electrons, and we're done. We're going to fill up the second S sublevel. Okay. Blair, why are you sitting back there? So when we get to the second primary level, we're going to fill up the S sublevel. Okay, so we filled up everything up to right here, and now we're going to move over to the P sublevel. And there are 3 orbitals in the P sublevel.
Oh, that's not 96. That's some little thing. There's the arrow. Yeah. Did it on them.
I should have put those 1 in a box and come back and pair them up. Then we get to the 3rd level, and we have S's and P sublevels in the 3rd level.
How many is it?
Then we come to the 4th level and fill up the 4S sublevel. But after the 4S sublevel, where potassium and calcium are located, we get to 3D. That's correct. 3D has 5 orbitals. And we're going to fill that entirely up, 1 on each orbital, come back and pair them up. And then after we get through 3D, we're back in the 4th primary level when we get to the P sublevel region over here. One in each box. Come back and pair them up. Now we get to 5S. And after 5S, then we go to 4D in here. And there are 5 orbitals in 4D. After 4D, now we get to 5P. And then we're going to go back and pair up all the electrons. After 5P, now we're going to have 6S. After 6S here, this is 5D. And we only need 1 electron for lanthanum. After 6S, you come to 5D. This is 6S right here. And then you drop back 1 level to get to, and when you get into this D sublevel region. And we don't do F sublevel regions, so at least in this class, so you don't that's as far as we need to go. All right, so that's the orbital notation. To the electron configuration, it's very similar, except that we don't write the boxes with the arrows. All we do is count the electrons in a sublevel and make that number a superscript. So for lanthanum then, for 1s here, it becomes 1s, and 2 electrons is 1s superscript 2. and 2s is 2s superscript 2. 2p is superscript 2, 4, 6 electrons. 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and 5d1. So that's the electron configuration, the full and complete electron configuration for lanthanum. To do the shorthand version, which is called the kernel version, or the sometimes the noble gas configuration, it's called a lot of different things. All we're going to do, we're going to take out whatever is the electron configuration for the next lowest noble gas, and replace that with the symbol for the noble gas in brackets. So if we look at this orbital or electron configuration here, this 5s2 and 5p6 is the end of the orbital or electron configuration for a noble gas. And in the fifth row, that noble gas is xenon. Okay? So all of this from here to here is the electron configuration for xenon. So to write the kernel, Kernal, electron configuration, we're going to put xenon in brackets like this, and then the remainder gets written next to it. You could do that, but you can look at this and see, if you see that you have a full S and P sublevel in a primary level, well, that's what you're going to have when you have a noble gas. And if you don't have a full S and P up here, and you work your way down, full S and P here, 5P and S, that means that must be a noble gas. And the noble gas in the fifth row is xenon. And that's how we know to put xenon here. Or you could write the complete electron configuration for xenon and take that part out. Or you could count up all the electrons and see how far you get to there. There's a lot of ways to approach that. Okay, so you can look at the noble gas here and see there are 54 protons, so there must be 54 electrons. You can count all the electrons in this electron configuration. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56. Well, we want to stop right there at 54, so that's one way to do it. That's fine. Okay. Now, if we're doing the electron dot notation, we're just going to count the electrons in the highest energy level. And there are 2 electrons in the highest energy level. So we're going to write lanthanum and put 2 dots around it. And there's your electron dot notation for lanthanum. The coefficient 6 here is the largest coefficient number in this electron configuration or orbital notation or this electron configuration. That means that this is the highest primary energy level, and all the electrons in the highest primary energy level, in this case, is just these 2 electrons. And that's how we get those 2 electron dots around this symbol here for the electron dot notation. So here's the kernel electron configuration for selenium. 4 is the highest primary energy level. In 4, there are 2 electrons here and 2 electrons here. So the electron dot formula has to have 6 electron dots for selenium. 2 here, 4 here, 2 here, 4 here is a total of 6 electrons in the 4th primary energy level. And so you need 6 dots in the electron dot notation for selenium. Right. If this is the nucleus of the atom, the first primary energy level is S, 1s. There's the 1s sublevel. Okay? Now these are spheres, they're not circles. Okay, you need to be able to think in 3 dimensions to really understand this. So you got the nucleus, and as you go out from the nucleus, you get to the first sublevel. That's S. It's in the first primary energy level. Okay? Then, in terms of the order that we put electrons into the way we think about it anyway, putting electrons into the electron cloud, the next thing we come to is the second primary energy level. So after 1s, you get 2s. Okay? Then you start filling up a p sublevel. P sublevels have 3 orbitals. So in the orbital notation that we've been working on, these are boxes. Okay? But when we look at the actual shape, the models we use in here, what we did in the activity in class yesterday was to make those models into the shape of a balloon. And we said a double balloon shape would be what a p orbital looks like. So this balloon and this balloon together makes 1 p orbital. This balloon and this balloon together makes 1 p orbital. This balloon and that balloon together make 1 p orbital. And they fit just inside the outer reaches of that S sublevel in the second primary level. So, 1s, 2s, okay. Pierre and Maurice Curie, because they were from Poland.
Yeah, let that run for a minute.
Okay, so 1s and 2s, and then you've got the 2p orbitals. Okay, so all of this right here is showing what's happening in the second primary level. This is 2s, and this is a 2p orbital, this is a 2p orbital, and this is a 2p orbital. Okay? And then after that, you go to the 3s sublevel. And in the 3s sublevel, inside the 3s sublevel region, you have 3p orbitals. Okay? So it just keeps building up. Now, if we go back to our 2s and p here, it's not the whole balloon that is the actual orbital. The actual orbital is the top half of these balloons. So it's the top half of that that's the actual orbital itself. Okay? What's missing out of that then is the 1s sublevel. Okay? That's what we're taking out of those 2p orbitals. So the 1s, the sphere that is in here, is not part of the p orbitals themselves. So you got to take that sphere out of the center here to actually see the actual shape. That's not really necessary for you to worry about on the test. This is the stuff you need to worry about on the test. Yes. So forth. Okay. I am not going to assure you that this key will be on the test. You need to know the nuclear formulas for alpha particles, beta particles, gamma radiation, and neutrons. You need to know that. Okay? All right? Now, I was asked to do 12 and 15 as an example here out of this worksheet. So let's do that. Okay? Now, you should know what particle has a mass of 1 and an atomic number of 0. Do you know? A neutron. Neutrons don't have any protons, so they don't have an atomic number. No, we're not grading this. We're just going over it. Okay? All right, so what element has 58 protons, guys? What element has 58 protons? Cerium. It's on your periodic table. The atomic number is at the top. The atomic number is the number of protons. So this is cerium. Okay? What is the atomic number for strontium? 38. It's on the periodic table. It's right here. There's strontium. There's the atomic number. That's the number of protons. That's what goes right here. Okay? What atomic number do we have for neutrons?
1 over 0.
Well, the atomic number is 0. What's the atomic mass? 1. What's the atomic number we assign to a beta particle? -1. It's not a real -1, but that's the number we assign to a beta particle. Okay? And what is the mass of a beta particle? Virtually 0, so we show 0. What we need to do now is to figure out how what the mass is for the total mass on the right-hand side, everything, and then figure out how we're going to match that mass over here. So what we're going to do is we're going to add up the masses across the top here. Okay? So we've got a mass of 144, a mass of 90, and a mass of 6 times 1, or 6. Okay? So 144. Well, if I can get it to work, here we go. 144 plus 90 plus 6. So I've got a total mass on the right-hand side of 240. Okay? I'm just going to put that on the top here on this worksheet so we can kind of see what's going on. All right, 240 is the total mass. Over on this side, this neutron has a mass of 1. I've only got one other particle, so what mass do I need here when added to this 1 is going to give me 240. 239. Okay? Now we're going to do the same thing with the numbers on the bottom, because all we're doing is keeping up with the number of protons on the bottom. So I've got 58, 38, 0, and I've got 2 times -1 down here. So 58 plus 38 plus 2 times -1 is a -2. Well, I got to use a negative symbol and not the minus button here. So there's a change of sign button there. And we're going to get a 94. Okay, so our atomic number on the right-hand side is a total of 94. This is 0, so what number needs to go there? 94. And what element has a atomic number of 94? The stinky element. Y'all know why I call it the stinky element?
No, does it smell bad?
No, it doesn't smell bad. Pu. Okay. Let's go down here and do number 15.
Wait, what happened?
All right, so number 15. What element has an atomic number of 96? Cm, which is curium. Okay. What element has an atomic number of 6? Carbon. If I have an element here and an element here, and they're putting together into making something larger, what is the process? What is the nuclear process that's going on here? 2 big particles squeezed together to make an even bigger particle? 2 smaller particles squeezed together to make a larger particle? Fusion. This is an example of fusion. Okay? All right. What particle has an atomic number of 1, atomic mass of 1 and atomic number of 0? Neutrons. Okay. Now we need to figure out from the mass up here what number goes down here. We've got 246 and 12. That comes out to be a total of 258. Okay? I've got 254 here. How do I get a mass of 4 AMU on this side in addition to this 254 so I can have 258? A 4 in front of the neutron. Now we'll have 258 on both sides. Okay, over here I've got 96 and 6. That adds up to a total of 102. Okay, and that's a 0. So what number goes here? Well, guess what? I could have looked it up because nobelium, NO, has a mass of 102. So it worked out. You know it's right. Okay? And so that's how you do it, guys. All right? Don't make it harder than it is. It really isn't that hard. Okay, just as an example, on the band of stability, which is what we drew in class, okay? If we look for element 50, it's right on this line right here. If you want to know which isotopes are stable, we just go and look at element 50, and on the left-hand side of this ruler here is where element 50 is, okay? And we compare that against all the numbers of neutrons, and you can see there are a lot of stable isotopes for 10, okay? Starting at where 10 has 60 protons, all the way up to where 10 has about, looks like 74 protons.
What is that?
I'm sorry, 7 neutrons. These are all neutrons on this side. 60 neutrons to 74. Now, there might be a gap in there somewhere, but I'm not going to expect you to know about where the gaps are, okay? I want you to know in general how to figure out what are stable isotopes and what are not, okay?
What is that line, the black line in the middle?
Black line in the middle. This line right here? Yeah.
That's where the stable is.
Between 1 and 20, between element number 1 and element number 20, can we please just turn down the volume? Between element 1 and 20, there are, roughly speaking, an equal number of protons and neutrons. That's what that line is about right there. Okay? That actually should be over here at 20. It's got misprinted, I guess. It should be at 20, not 10. Okay? And really, after about 15. So early on, it starts to nose its way up. Okay? So then after that point, then you can see how it curves slowly upward till we reach a point up here where we're roughly 1.5 times more neutrons than protons. And that's what's at the top up here. And that's all I ask you to do is draw that out, draw those boundaries on your sheet yesterday, and be able to draw that curve so you can kind of figure out, estimate what would be stable isotopes and what would be not stable isotopes. Okay? All right.
I forgot where you subtract. Can you tell me what's your rule?
If you have an isotope, a nuclear symbol for an isotope, let's say we had uranium-238. Okay? This is the number of protons. If you want to know the number of neutrons in uranium-238, you have to subtract this number from that number because the mass is the sum of protons and neutrons. So if that's the sum, we subtract to undo. If you're looking on this on the band of stability, yes, but the thing to remember is uranium has an atomic number of 92, and the stable isotopes only go up to 82. So this would not be on here. If we were using, say, selenium 79, and selenium has atomic number 34, well, that would be on here. Okay, so 34 is right here, and you subtract this number from that number, and you get 30. Let's see, what is it? 45? Is that right? 45. So it's 45. So 35 and 45, and find out whether it meets right there or not. Okay, that's what we're using that for.